Okay, hi everyone. My name is Alex, and today I'm going to tell you about a small piece of some recent work we did. And in particular, I'm going to tell you about a piece that's relevant to how you can verify VDFs inside of SNARKs. This is joint work with Dan, and with Riyadh, and with Barry. So the beginning of this story is with the Wesolowski proof of exponentiation, like so many of our work. Um, and so the setting here is that we're trying to claim that when you square x n times, you get y. And non-interactively, the way that you would go about doing this is that you take x and y and n, all the inputs, you put them into a hash function. This hash function spits out prime numbers that importantly have 2 times lambda bits of entropy. We're going to model this as a random oracle. And then the prover computes the proof, which is q, which is x raised to the power of 2 to the n divided by L. And importantly, this division is integer division, which means that it discards the remainder. So the intuition here is the prover is doing like almost all of the work, and you're going to use this to confirm that the VDF was computed correctly in a moment. So yeah, the verifier goes ahead and computes L for themselves, and computes 2 exponentiations and a product, and does an equality check. So this is just a rehash of what we've heard already a million times. The observation that we make is that this is nice because the verifier is not doing like an unimaginable amount of work, but they're still kind of doing a lot of work. These are exponentiations, and they're kind of expensive. And so the observation is that one thing you could do if you were interested in making it even easier for a verifier to check the VDF is you could actually have the prover write a succinct proof that verification evaluates correctly. So you could take this whole picture and you could put it inside of the SNARK. And in order to do that, we have to re-envision the verifier's operations in circuit form. So drawing the circuit, we start with the inputs x and y. For now, we're going to assume that we've fixed n to be some constant that we agree upon in advance. We're going to bake it into the circuit. So you take the remaining inputs x and y, and you feed them into this hash function that's supposed to spit out a prime number. And then you compute 2 to the n mod the output of the hash function. And so there's a whole bunch of modular squarings going on over here, log n of them. And then you compute the exponentiations in the group, and you compute the product in the group, and you do an equality check. So this is the circuit layout of Wesolowski's verifier. And the observation that we make is that basically there are 2 kinds of things going on here. One, you have a hash function that outputs prime numbers. We call this hash to prime. And that's in the left-hand corner. This is how you get the challenge for the Wesolowski proof. Then we also have a whole bunch of multi-precision arithmetic. This is the stuff that we've been working on in the hardware context and is also present here. And so what I'm going to do for the rest of this talk is go into some detail on how we design hash to prime inside of a SNARK. And then I'm also going to give just a taste of how you do multi-precision arithmetic inside of a SNARK, because that's more technical and also builds a lot on prior work. So let's start with hash to prime. So the strawman solution here is sort of the classic solution on CPUs, which is hash and check. And so what you do for hash and check, this is a classic idea, is that you choose some base hash function, consider SHA, for example, SHA-256, and then you define the hash of x to be h of x concatenated with n, where n is the smallest number such that this is prime. So in some sense, this seems like a pretty minimal definition, and it kind of is. What you have to do is you just have to find this n, the smallest n that produces a prime hash. And in order to do this, you have to test a whole bunch of numbers for primality. Because for every n, you produce a hash, and you have to check, is this prime? And so as an example of a primality test, you might use Miller-Rabin, which is a probabilistic primality test in which you choose, you run many rounds, and in every round you choose a random integer a, and you do an exponentiation to the p minus 1 mod p, where p is this claimed prime. And in order to have this be sound, you need to do a whole bunch of rounds. So you're going to be doing many exponentiations. And this is the problem with this approach inside of a SNARK, which is that these primality tests are actually rather expensive. You have to do a lot of exponentiations, and you have to do many rounds of this. And so our goal was to try to find a technique for doing hash to prime that enabled the verifier to do less exponentiations, to do less work inside of the SNARK. And the idea for how we pursued this is to exploit primality certificates. And so the primality certificate that we used is called Pocklington's criterion. And so that if you don't know, the idea behind a primality certificate isn't that you just give somebody a number and have them check that it's prime. You give them a number with a certificate that certifies its primality. And the idea is the certificate should be easily checkable. So Pocklington's criterion is a mathematical statement that gives us a primality certificate. You can think of it as a partial converse to Fermat's little theorem. And what it says is that if p is a prime and x is some number less than p, and we have a particular relationship that holds for some exponentiation. I'm not going to go into the details of this right now. And you also have a GCD relationship. Again, I'm not going to go into the details. Then the product of x and p plus 1 is prime. So for here, I think what we should do is sort of take the 1,000-foot view. And the 1,000-foot view here is that Pocklington's criterion allows you to write certificates of the form p, x, and a, which are certificates for the primality of p prime equal to xp plus 1. And x can be as large as p, but not larger. And then there are some conditions that you have to check to verify that the certificate is good, but these conditions are essentially one exponentiation. That's the heavy work here. So what I want to emphasize is that this allows you to, in some sense, double the size of your prime, because x can be as big as p. So if you're interested in trying to find a larger p prime, you can imagine randomly sampling x and sampling it to be almost as big as p, but not quite as big as p. So the fact that you can double the size of your primes in this way suggests that you might be able to construct recursive Pocklington certificates of large primes, where you start with some base prime, p0, which maybe you verified as prime using a lookup table or using some other primality test, and then you bootstrap your way to larger primes, doubling the bit width each time. And each time you're using a Pocklington certificate. So what you end up with is this recursive Pocklington certificate that's based on some sort of base primality notion. So more concretely, the way that we instantiate this is that we choose a base hash function h. We use hash and check to produce a 32-bit prime, p0. And we're going to check this with Miller-Rabin. So there's a deterministic variant of Miller-Rabin that works for 32 bits and runs super fast because 32 bits is not very many. So we do hash and check to come up with a 32-bit prime. And then we do hash and check not to come up with large primes, but to come up with x's, such that a valid Pocklington certificate can be constructed. And we repeat this until we get a prime that has as much entropy as we want. And so here, when we do a breakdown of the costs, well, we have to start with this 32-bit Miller-Rabin check, which is not very expensive. And then at each level, we have to do an exponentiation and a coprimality check and a comparison. These are all the conditions of the Pocklington criterion. And the high order bit here is the exponentiation. So at each level, we do one exponentiation. And that means that at the end of the day, if we're trying to produce some prime number that is 250 bits or 256 bits, then we're going to have to do an exponentiation that's that wide, but we're only going to have to do one. And we're going to have a guarantee that this number is prime. It's not probabilistic. This is a downside, and the downside is we're doing more hashing and checking, which means that we need more nonces to verify that this protocol is, or to improve the completeness of the protocol. That means that we're going to pick up some extra bits along the way, and some of our numbers are going to get bigger. It's okay. We can deal with it. Okay, so this is a sketch of how we do hash to prime inside of a SNARK. Of course, it builds on multi-precision arithmetic because we're doing all these exponentiations and coprimality checks. So that takes us into the second part of this talk, which is just a brief taste of how we do multi-precision arithmetic. We have a question in the back.
Don't we lose the determinism? Because you wanted it to be the very first nonce.
Yeah. So great question. And the question is, I think the answer is, do we need determinism in this context? And so what we want is we want a challenge that has very high entropy, but it doesn't actually have to be unique. As long as its entropy is so high that the prover cannot meaningfully control its value. And then this certificate does have that property. And so then, of course, the question is, how do you know that the verifier is going to get the same prime as the prover? And the prover is going to provide its work, right? It gives you the certificate, so you're going to end up with the same value. Great question. Yeah, so in some sense you can pick your prime, but you're picking your prime from one of 2 to the 256 buckets where you don't control what bucket you're in. So I guess that's on your side here. And this means that the guessing entropy is still very good. It occurs to me that maybe I'm going a little bit too fast. Okay, we'll move along. Okay, so multi-precision arithmetic. Why do we need this? Just a recap. I already said for the hashed prime stuff, we're doing all these different operations, GCDs, exponentiations, comparisons. Also, looking back at the Wesolowski circuit, in that circuit, we have modular multiplication explicitly. We also have products in the group of unknown order and exponentiations in the group of unknown order. And our group of unknown order, at least when we were working on this, we defined to be an RSA group mod, the subgroup generated by -1. So that means that those operations also boil down to modular operations. So basically, to first order, everything comes down to doing modular multiplications, and that's what I'm going to tell you a little bit about right now. So let's think about how we do this. So modular, and I should also say this work, we contributed a little bit, but a lot of this is prior work from XJ SNARK. So the stuff I'm presenting here is some them and some us, but I mention it because I think this stuff is interesting, and I guess we're going to do a breakout session on this later today, and this is the kind of stuff we want to improve. Okay, so we have a modular multiplication. We want to verify the equation that x times y is congruent to z mod n. How do we do this? We imagine rewriting it as an existential statement about integer multiplication. So what are we saying? We're saying that there exists some k such that nk is the offset that satisfies this equation. And the important thing here is that we've rewritten this just in terms of multiplication. So notice we have a product x times y and a product n times k, and then also an addition. So we've reduced the problem to verifying multiplication for big numbers. And so how do we do that? Well, we break our numbers up into limbs. I guess limb is the word for a chunk in the world of multi-precision arithmetic. Sounds kind of morbid to me. Anyways, so we break our numbers up into limbs. So here I have 2 numbers a and b, and I've written them as 3 limbs each. So we're asserting that we have some upper bound on the size of the numbers, which is fine. This is modular arithmetic. We do have an upper bound. It's the modulus. And what do we do? Well, I'll do a little bit of a forward reference. What we're actually going to do is we're going to take these limbs, and instead of interpreting them as limbs, we're going to interpret them as the coefficients of a polynomial. And we're going to do polynomial multiplication. This isn't quite integer multiplication because, of course, polynomials don't carry. So after we do polynomial multiplication, we're going to go ahead and use a carry circuit to fix up all the limbs. And the carry circuit is sort of linear size, just like on standard hardware. And so the real question here is polynomial multiplication. Can we do that really fast? Can we do that really small? And the answer is yes. Before we talk about that, though, I want to say a bit about how you sort of make the carry work well. And the answer is that you take some techniques from compiler development. You do range analyses. You keep track of a lot of metadata about all the numbers that you're working with, and use that to shrink these carry circuits and make them as small as you can. So this is like technical, but sort of where a lot of the magic is. If you do this stuff well, then this is efficient. If you do this stuff badly, then you pay a pretty high cost. So these sorts of range analyses end up being really important. But equally important is the polynomial multiplication. So let's talk about that. So we have an abstract constraint that we want to verify, which is that the product of 2 polynomials is a third. And we've gone ahead and we've encoded these polynomials as sequences of coefficients. These are the limbs from our natural numbers. And the way that we actually translate this to rank 1 constraints is as follows. We go ahead and check that the polynomials evaluate. So the product and the polynomial, we check that they evaluate to the same value at a number of different constant inputs. So we choose small constant a's and check that f of a times g of a is equal to h of a. And the reason why this is useful is that checking polynomial evaluation at a constant point is very efficient inside rank 1 constraint systems, because polynomials are linear functions of their coefficients. So this is just an example of what this ends up looking like. The thing I want to emphasize here is that, so for example, when this last row is when a equals 5, we just go ahead and plug in, when a is 5, we just put in a 5 for x. And when it's 5, we put in 25 for x squared, and so on. So this is sort of like an old trick that you can do inside rank 1 constraint systems, and here we can use it to do fast polynomial multiplication, or I should say small polynomial multiplication, because we're thinking in terms of circuits. Okay, so this is like a sort of a whirlwind overview of sort of like the more interesting core of how you do multi-precision inside SNARKs. Obviously, there's some opportunities for optimization here, and I would love to talk to people about that later this afternoon. I want to give you a sense of kind of like what the numbers boil down to. Again, a rough sense. So a few things. So the hashing to a 256-bit entropy prime using these techniques ends up being something like 750,000 constraints. If the prime is smaller, of course, you save some. And that cost really is dominated by the exponentiations that you have to do. A proof of exponentiation check in total, without the hash, which is separate, comes out to around 5 million constraints. In our work, it's 10 million, because we have to do 2 of these. But if you're just doing a VDF verification, it's going to be around 5 million. And then I also have the costs of group exponentiations and group operations up here as well. Again, this is the way that we implemented it. I bet we could find better ways to do it. Would love to talk to people about that. If you guys want to look at the implementation, it's online at that URL. And then just an overview of what I think are the opportunities to do this better. Justin listed a few earlier, and just a few more. If there's some way of doing better range checks, maybe with custom gates, this would be huge. So these numbers, like 80% of these constraints are just doing range checks, repeatedly checking that different values are less than 32. Less than 2 to the 32. If we could do that better, these costs go down dramatically. And then other things is that this, when we did this work, we weren't optimizing for VDFs. We were doing more general proofs of exponentiation. There might be some tricks that we can play. For example, taking advantage of the fact that maybe the modulus is constant and can be baked into the circuit or something like that. Yeah, and maybe I'll leave it at that for now. Okay, so I'm happy to take any questions. In the back, Ariel.
The Pocketing thing, it is deterministic when the criteria is satisfied. So why can't you stop every time when at the first time the?
Yeah. Okay. Yeah. This is a great subtlety. So if the hash function as we defined it is to find the first nonce such that Pocketing's criterion is satisfied, then that protocol is deterministic. But the verifier is not going to check that the nonce you provided is the first valid one.
Oh, okay.
So in some sense, from the verifier's perspective, it's not deterministic, and from a security perspective, we shouldn't treat it as that. But from sort of like honest parties agreeing on stuff perspective, yeah, it's deterministic.
Okay, thanks.
You mentioned that the hash output is like slightly bigger than the other techniques, and from what I understand, if you have many, for example, VDF proofs to verify or like docs, then generally there's an asymmetry between the number of hash primes, which is just 1, and then the number of exponentiations. And so would it be plausible that given sufficiently many exponentiations, actually you're better off to invest in a small prime upfront?
Yeah, absolutely. So again, it would depend on sort of how the numbers break down. But if you're going to be multiplexing one hash to many proofs, that might be a good idea. Yeah, that's an interesting direction. In that context, I think it's a cool question whether you can do better than Miller-Rabin. I would hope that you could. Okay, awesome. Thank you guys.
Thank you.